Lay back. Make yourself comfortable beneath the soft light of your room. Close your eyes and let your thoughts drift slowly, like starlight across an empty sky. What does it feel like when something from another star system drifts into our own? Silent, unseen, and older than nearly every world we know. Far beyond the edges of our familiar planetary orbits, something unusual appeared. On July the 1st, 2025, a telescope perched on a quiet hillside in Rio Hurtado, Chile, paused for a moment, then captured a faint speck of light moving against a backdrop of distant stars. That speck, later named 3I Atlas, would soon prove itself not just another wanderer among asteroids and comets, but an interstellar visitor traveling on a path that began long before the sun formed. Content reference: OASITE. Index Swarm 1. In the hours following its discovery, astronomers studied its motion. The object was located several astronomical units from the Sun, beyond the orbit of Jupiter, and yet it moved with a velocity that no gravitational tether could contain. Its trajectory did not curve into a stable orbit. Instead, it followed a hyperbolic path, plunging toward the inner solar system and then destined to depart forever. Content reference: OASITE. Index 2. As word spread through observatories around the world, more eyes turned to the skies. Data that had already been collected by other telescopes, images taken only days or weeks before, were quickly re-examined. There on archival plates, faint traces matching the motion of 3I Atlas were found. These pre-discovery observations extended the record back several weeks before the official report, confirming that this object had been traveling steadily toward our Sun before anyone realized what it was. Content reference: OASITE. Index 3. The significance became clear. This was only the third object ever observed to come from outside our solar system, after two earlier visitors. But unlike some silent wanderers, 3I Atlas displayed signs of activity. As astronomers continued to monitor it, faint hints of a fuzzy coma, a diffuse envelope of gas and dust, began to emerge, indicating the presence of volatile ices sublimating under sunlight. Content reference: OASITE. Index is 4. Evolving from a tiny speck into a slowly brightening object, 3I Atlas invited questions. Where had it come from? What kind of star system had launched it across the vast gulf of interstellar space? And what could its ice and dust tell us about distant planetary systems? Already, its arrival had transformed our solar neighborhood into a brief crossroads, a place where the quiet orbits of familiar planets intersected, however fleetingly, with a visitor from the deep galaxy. In that moment, humanity was given a rare chance to glimpse, in passing, a fragment of some other star's history. The path of 3I Atlas was calculated with care, relying on precise measurements of its changing position against the stellar background. Each observation, taken at different times from observatories spanning the globe, allowed astronomers to determine its velocity relative to the Sun. Unlike planets or comets bound within the solar system, 3I Atlas moved faster than the escape velocity at its distance, a clear indicator that it originated elsewhere. Its orbit was not elliptical, but hyperbolic, with an eccentricity greater than 1, meaning it was destined to continue outward indefinitely. Observatories collaborated, sharing both optical and infrared data to capture as complete a picture as possible. Despite the faintness of the object, subtle variations in brightness revealed information about its shape and rotation. Photometric studies suggested It was small, likely only a few hundred meters across, and irregular, with light curves indicating a tumbling motion rather than a simple spin. The interplay of sunlight across its surface, reflecting differently from various angles, provided the first hints of its composition. Spectroscopic measurements were more challenging. The faint signals required long exposures, careful calibration, and the alignment of multiple instruments. Yet even in the limited spectral data, scientists detected subtle absorption features consistent with volatile compounds, likely ices such as water, carbon monoxide, and carbon dioxide. Dust particles, released as these ices sublimated, contributed to the diffuse glow observed around the nucleus, resembling the coma of a typical comet. The composition, while broadly similar to comets within the solar system, carried subtle distinctions that hinted at a different formation environment. Tracing the motion of 3I Atlas backward through space suggested it had traversed immense distances before encountering the Sun. Its incoming trajectory pointed roughly toward the constellation Taurus, but stellar motions over millions of years complicate any attempt to pinpoint its origin precisely. Close encounters with other stars, gravitational perturbations from the galactic disk, and the intrinsic motions of the interstellar medium all make it impossible to determine a unique source. Instead, astronomers can only assign probabilities to its passage near young stellar associations or star-forming regions where ejection events might have occurred. The interstellar medium itself is not empty. As 3I Atlas crossed it, it would have been exposed to cosmic rays, magnetic fields, and sparse clouds of gas and dust over millions or even billions of years. These interactions may have altered its surface chemistry, producing a thin layer of irradiated material. This exposure, combined with the thermal effects of stellar passages, helps explain some of the observed differences from objects native to the solar system. Even in its brief encounter with the Sun, the solar radiation began to erode this ancient surface, releasing tiny grains of dust into the surrounding space. 3I Atlas's arrival was also a reminder of the limitations of our observational technology. Most interstellar objects, especially small and faint ones, pass undetected, slipping through the sky unnoticed. Current surveys like ATLAS and Pan-STARRS monitor the heavens systematically, yet they only catch a fraction of such visitors. This detection, however brief, allows astronomers to sample material from distant star systems directly, providing insights that cannot be gleaned from meteorites or telescopic observations alone. Future observatories, including the Vera C. Rubin Observatory, are expected to identify more interstellar travelers, expanding our understanding of the diversity and frequency of these cosmic emissaries. Even as 3I Atlas receded from view, its fleeting passage contributed to an evolving picture of the galaxy. Astronomers consider not only the physical characteristics of the object, but also its broader context: how planetary systems form, how debris is ejected, and how material circulates between stars. Its journey, though measured in months within the solar system, represents a voyage spanning millions of years and countless parsecs, connecting distant stellar nurseries with our own planetary neighborhood in a subtle, silent exchange. The motion of 3I Atlas through the solar system was tracked with increasingly precise astrometry. Observers measured tiny changes in its position night after night, refining calculations of its hyperbolic orbit. The data revealed a trajectory that approached the Sun at a steep angle, entering from above the ecliptic plane and swinging past the inner planets at a distance that ensured no interaction with their gravitational fields. The velocity at infinity, the speed it carried beyond the sun's influence, was several tens of kilometers per second faster than typical solar system objects, a clear signature of an interstellar origin. Efforts to trace the object's prior journey relied on simulations of galactic dynamics. Using known stellar motions and models of the Milky Way's gravitational potential, astronomers attempted to reconstruct probable paths over millions of years. The results were inherently uncertain, yet they suggested that 3I Atlas may have originated from a relatively young stellar cluster, where gravitational interactions and planetary migrations are known to eject debris. Even so, the immense timescales and chaotic perturbations meant that no single star could be definitively identified as its source. The faint glow of 3I Atlas provided subtle but revealing information about its surface. As the object approached the inner solar system, the increase in solar radiation caused volatiles to sublimate, producing a sparse but detectable coma. Unlike the dramatic comets familiar in our skies, this activity was minimal, reflecting both the small size of the object and the composition of its surface layers. Observers measured the reflected light to estimate its albedo, which appeared low, suggesting a dark carbon-rich surface, similar in some respects to primitive cometary nuclei within the solar system, but also consistent with prolonged exposure to interstellar cosmic rays. Spectroscopic studies added further nuance. Absorption features indicated the presence of simple molecules, such as water ice, but the relative strengths differed from those commonly seen in solar system comets. Such variations are expected when materials form in environments with distinct temperature gradients, radiation exposure, and chemical abundances. The surface may be coated with refractory dust, a residue of sublimated volatiles and micrometeoroid bombardment accumulated over eons, giving the object a muted, almost featureless appearance in some spectral regions. The trajectory of 3I Atlas was mapped relative to the planets, but the object remained largely imperceptible to the naked eye, detectable only with large, sensitive instruments. Its fleeting passage emphasized the limitations of even sophisticated sky surveys. The discovery underscored the importance of rapid follow-up observations. Each additional measurement extended the observational arc, reducing uncertainties and allowing more precise modeling of both its current path and potential origin. International collaboration enabled round-the-clock monitoring, ensuring that as the object receded, valuable data continued to be collected. Comparisons to previous interstellar visitors provided context. The first, 1I Oumuamua, exhibited unusual acceleration without visible outgassing, while 2I Borisov displayed clear cometary activity. 3I Atlas appeared less extreme than either predecessor, but shared characteristics with both, reinforcing the diversity of interstellar material. Observations of its rotation, brightness variations, and sparse activity allowed scientists to refine models of small body physics, particularly for objects that have traveled far beyond their parent systems. The environment through which 3I Atlas traveled also contributed to its observed characteristics. Long exposure to galactic cosmic rays would have altered surface chemistry, potentially creating a thin crust of complex organic compounds. Interstellar dust, though sparse, may have eroded surface features over millions of years, gradually modifying its shape and reflectivity. These processes operate slowly, but over cosmological distances, their cumulative effects are measurable, providing indirect insight into the history of material outside the solar system. Despite its modest size and fleeting visit, 3I Atlas offered a rare opportunity to study the composition and dynamics of material originating in other planetary systems. Each observation, each measurement of light and motion contributed to a growing understanding of how objects are ejected from star-forming regions, how they traverse the galaxy, and how they interact with other stellar systems along the way. Even in its brief solar passage, 3IR Atlas became a messenger from the galaxy, carrying information encoded in ice, dust, and trajectory, silently bridging the space between stars. Astronomers turned next to modeling the past trajectory of 3I Atlas, combining precise astrometric data with computational simulations of stellar motion within the Milky Way. By integrating the object's hyperbolic orbit backward in time and accounting for the gravitational influence of nearby stars, clusters, and the galactic disk, they created probabilistic maps of its potential origins. The results suggested multiple candidate regions within several hundred parsecs, often associated with young stellar associations or dense star-forming complexes. Environments where gravitational interactions and planet formation processes can readily eject debris into interstellar space. Yet even with the most detailed models, the chaotic nature of galactic dynamics over millions of years prevents a definitive identification of a parent star. The hyperbolic excess velocity of 3I Atlas, measured at the point where the Sun's gravitational influence becomes negligible, was particularly informative. This velocity, approximately 32 kilometers per second relative to the Sun, was higher than typical solar system escape velocities, but consistent with expectations for interstellar objects that have been accelerated through interactions with massive planets or neighboring stars before being cast into the void. Such speeds also influence the duration and detectability of the object within the inner solar system, compressing the observational window and emphasizing the fleeting nature of these visits. The orientation of 3I Atlas's trajectory revealed subtle clues about its long journey. Approaching from a direction roughly toward the Taurus Auriga region, its path intersected the ecliptic plane at a steep angle, minimizing gravitational perturbations from the planets. The inclination and approach vector, when combined with models of galactic stellar motion, helped constrain the range of plausible origins, though even the nearest candidate stars lie thousands of light-years distant. Each calculation illustrates the difficulty of tracing material across the galaxy with absolute certainty. Yet even probabilistic connections provide valuable context for understanding interstellar dynamics. Observational campaigns sought to characterize the object's physical properties with high fidelity. Multi-band photometry, conducted across optical and near-infrared wavelengths, revealed a slow but measurable variation in brightness over hours, consistent with a rotation period on the order of several hours. The light curve displayed asymmetries indicative of an irregular, elongated shape rather than a compact spheroid. This tumbling motion, combined with faint outgassing signals, suggested that surface layers of volatile ices were unevenly exposed to solar heating, a pattern expected for objects that have endured long-term cosmic ray irradiation and micrometeoroid erosion. Spectroscopy, despite the faintness of the object, confirmed the presence of subtle absorption features. Water ice dominated the observed spectrum, with weaker signatures consistent with carbon monoxide and traces of other simple volatiles. The low albedo, approximately 0.04, suggested a dark, carbon-rich surface, similar to D-type asteroids, but chemically distinct due to prolonged exposure to interstellar space. Thermal models indicated that the surface temperature remained low enough during its solar passage to prevent rapid sublimation, contributing to the subdued appearance of the coma and making direct compositional inferences more challenging. 3I Atlas also offered a unique opportunity to refine models of interstellar small body populations. By comparing its observed properties, size, reflectivity, activity, rotation, to those of Oumuamua and Borisov, astronomers began constructing preliminary distributions of interstellar object characteristics. These comparisons indicated that such objects can vary widely in composition and structure, reflecting differences in formation environments, ejection mechanisms, and galactic exposure. Even within a small sample, the diversity underscores the importance of each detection in constraining the broader picture of galactic debris. The interstellar medium through which 3I Atlas traveled contributed to its observed state. Cosmic rays gradually alter surface chemistry, producing thin layers of complex organic compounds, while sparse gas and dust can abrade surfaces over millions of years. The object's structure and composition, therefore, are not only a record of its origin, but also a chronicle of the conditions it encountered across the galaxy. By studying these subtle effects, scientists can infer the cumulative impact of interstellar environments on small bodies, providing insight into the processes that shape material before it ever encounters a planetary system. Even as 3I Atlas receded from the inner solar system, its significance persisted. The faint glow observed during its passage, the slow, tumbling rotation, the traces of volatiles, all contribute to an understanding of how matter circulates between stars. Each measurement enriches models of planetary system formation, of the mechanisms that eject debris, and of the subtle interactions that govern long-term survival across interstellar distances. In these quiet observations, humanity gains a direct connection to distant regions of the galaxy, a fleeting but tangible encounter with material older than our sun, traveling at speeds that hint at the vastness of the spaces between stars. As 3I Atlas drew closer to the sun, subtle changes in brightness revealed the influence of solar radiation on its surface. The gradual warming caused the faintest release of gases from exposed ices, producing a tenuous coma that spread lightly into space. Observers noted the absence of prominent jets or tails. The activity was minimal, yet measurable, a reflection of both its small size and the slow sublimation of volatiles. Even the faintest emissions were meticulously recorded, providing data critical for understanding the thermal response of interstellar material under solar heating. The orientation of 3I Atlas relative to the Sun and planets determined the geometry of observation. From Earth, telescopes tracked the changing angles, adjusting for parallax and accounting for motion against a dense field of background stars. Each frame added incremental precision to the trajectory, allowing scientists to refine estimates of its rotation period and axial tilt. Variations in reflected light indicated that sunlight fell unevenly across its irregular surface, confirming the irregular, elongated structure inferred from earlier photometric studies. Its passage also offered insight into the limits of current detection capabilities. The object reached maximum brightness for a brief period, still faint enough that only instruments with large apertures could capture meaningful data. This ephemeral visibility underscores the likelihood that many interstellar visitors cross the solar system undetected, hidden by distance, size, and faint albedo. Each discovery, therefore, represents a rare opportunity to study material from beyond the Sun's influence, and the lessons learned are extrapolated to estimate the broader population of such bodies in our galaxy. Thermal modeling, combined with observational data, provided constraints on surface composition. Low albedo, minimal outgassing, and slow sublimation suggest a crust enriched in refractory organics layered over more volatile, rich interiors. Such a configuration is consistent with prolonged exposure to cosmic radiation and interstellar dust, which gradually alters surface chemistry while leaving deeper layers relatively unmodified. These subtle chemical gradients carry records of the environments the object traversed, offering indirect insight into the conditions present in other planetary systems. Comparisons with 2I Borisov highlighted the diversity of interstellar objects. While Borisov displayed robust cometary activity with a visible tail, 3I Atlas remained comparatively quiescent, reinforcing the idea that small bodies ejected from other systems can manifest widely different behaviors when encountering the Sun. In combination with Oumuamua's peculiar characteristics, these observations illustrate a spectrum of possible compositions, shapes, and responses to stellar heating, enriching the framework used to model interstellar populations. Observations continued as the object moved away from the Sun, entering a region where solar radiation weakened and sublimation ceased. The coma gradually dissipated, leaving behind a faint reflective core, observable only through sensitive instruments. Scientists documented this fading carefully, as the decline in brightness provided additional constraints on size, albedo, and dust-to-gas ratios. Even as it receded, the object's trajectory continued to offer clues about the past, helping refine models of motion and the effects of gravitational perturbations from the Sun and planets during its brief passage. Beyond the immediate solar system, 3I Atlas carries lessons about galactic material exchange. Objects like this are ejected through planetary scattering, close encounters, and stellar evolution processes, traveling vast distances before any chance encounter with another star. Its brief visibility demonstrates the interconnectedness of star systems, the movement of solids through the galaxy, and the potential for interstellar debris to deliver material between planetary systems. Every measurement contributes to understanding these subtle but persistent processes, revealing a quiet, ongoing dialogue between stars mediated by small, traveling bodies. The passage of 3I Atlas also informs the design and operation of future surveys. The object's faintness, rapid motion, and brief window of observability highlight the need for sensitive, wide-field monitoring, capable of detecting even the smallest interstellar wanderers. By analyzing detection rates, brightness distributions, and orbital parameters, astronomers refine the criteria for identifying interstellar candidates in real time, increasing the likelihood of capturing such fleeting visits and expanding our catalogue of galactic travelers. Even as the object disappeared into the depths beyond Neptune, it left an indelible mark on the scientific record. Observations recorded across continents, spanning multiple wavelengths, and interpreted through the lens of decades of astrophysical research, coalesced into a detailed understanding of its composition, motion, and interstellar history. In its silence and subtlety, 3AI Atlas spoke volumes about the processes shaping planetary systems across the galaxy, offering a tangible connection to the vast, dynamic expanse that stretches between stars. Beyond the immediate influence of the Sun, 3I Atlas resumed its steady journey through the interstellar medium, a passage largely unchanged for millions of years before its encounter with the solar system. Along this route, it would have been exposed to a constant flux of galactic cosmic rays, high-energy particles that gradually penetrate and chemically alter surface materials. Over time, these interactions produce complex organics, a thin layer of irradiation products coating the ice beneath, preserving a record of the object's long sojourn through the galaxy. The slow accumulation of these compounds modifies surface reflectivity, affecting observational measurements and providing a subtle fingerprint of the cosmic environment through which it has traveled. Interstellar dust also contributes to the slow evolution of such objects. Sparse though it is, dust particles impacting the surface at high velocities erode microtopography, smoothing sharp edges and redistributing loose material. These processes, operating over millions of years, subtly reshape the surface, blending chemical history with physical modification. The combination of irradiation and erosion allows scientists to interpret observed spectra and albedo with greater nuance, revealing the cumulative effect of interstellar exposure. The origin of 3I Atlas likely lies in a system distinct from our own, where planetary formation and gravitational dynamics created conditions capable of ejecting small bodies. Scenarios include interactions within tightly packed young planetary systems, scattering events among giant planets, or perturbations induced by passing stars. Each mechanism results in slightly different ejection velocities and trajectories, and while the exact pathway remains uncertain, the physical characteristics of the object, size, composition, and structure, align with predictions from models of ejected material. These insights inform broader theories about the frequency and nature of interstellar debris and the processes by which planetary systems exchange material. By comparing the properties of 3I Atlas with other interstellar objects, astronomers refine statistical estimates of the population of such bodies within the Milky Way. Its small size and low brightness suggest that many similar objects pass through the solar system unnoticed, implying a vast, largely hidden population. Modeling these populations requires combining detection statistics with dynamical simulations, accounting for the relative motions of stars, the efficiency of ejection processes, and the survival rate of small bodies over galactic timescales. Each detection, therefore, serves as a critical data point, anchoring theoretical models in observation. The physical behavior of 3I Atlas during its brief solar passage adds further depth to these models. Minimal outgassing and subdued coma formation suggest a surface depleted in highly volatile ices, or possibly covered with a refractory crust built over millennia. The tumbling rotation indicates that the object has experienced torques over time, likely from outgassing or collisions prior to ejection. By examining these properties, scientists can infer not only the current state of the object, but also the conditions of its early system and the evolutionary processes it underwent during its long interstellar journey. Observations of light curves and spectral features also provide insight into internal structure. Variations in brightness correspond to irregular shape and heterogeneous surface composition, while the absence of pronounced cometary jets suggests either a lack of subsurface volatiles near the surface or a depletion from prior activity. This combination of characteristics implies a robust, ancient body capable of surviving millions of years in the harsh environment between stars. Its persistence offers a tangible example of how small bodies can endure across vast interstellar distances, serving as messengers from distant planetary systems. The interstellar trajectory of 3I Atlas reinforces the dynamic nature of the galaxy itself. Stars move through the galactic disk, interacting gravitationally, while planetary systems evolve, ejecting material at varying speeds. Small objects like 3I Atlas are subject to these forces, wandering from their parent systems, carrying physical and chemical records across hundreds or thousands of light years. Their presence in the solar system, even briefly, provides an opportunity to study these processes directly, linking the microscopic properties of ice, dust, and organics to macroscopic galactic dynamics. Every measurement made during its passage contributes to a cumulative understanding of these distant processes. Data from multiple observatories, interpreted through models of thermodynamics, spectroscopy, and celestial mechanics, converge to create a coherent picture of the object's history. Its rotation, surface chemistry, trajectory, and minimal activity are not isolated phenomena. They are interconnected indicators, revealing both the conditions of its origin and the environment it has navigated over eons. The object's journey, though measured within the solar system in months, reflects the scale and complexity of galactic interactions that span millions of years. 3I Atlas's passage through the solar system underscored the immense scientific value of even fleeting encounters with interstellar material. Each photon collected, each spectral line measured, and each positional data point contributed to a nuanced understanding of bodies that have traversed the galaxy over millions of years. Observatories around the world coordinated to maximize coverage, employing optical, infrared, and even radio observations where possible. By combining datasets from diverse instruments, astronomers were able to refine estimates of its size, shape, composition, and rotation with unprecedented precision for such a transient visitor. These combined observations revealed that its surface was not uniform. Subtle variations in reflectivity indicated regions with slightly different compositions or textures, possibly the result of localized sublimation, cosmic ray irradiation, or micrometeoroid impacts accumulated over vast distances and timescales. The rotational characteristics of 3I Atlas were particularly informative. Light curve analysis suggested a rotation period of several hours, but the brightness variations did not repeat symmetrically, implying a complex tumbling motion rather than a simple spin around a single axis. Such non-principal axis rotation is consistent with long-term exposure to external torques, whether from past sublimation events or collisions in its parent system prior to ejection. This tumbling complicates models of thermal evolution, as different surfaces receive varying amounts of solar radiation during rotation, influencing the rate of sublimation and the potential development of a coma. Yet even within these subtle variations, astronomers gleaned information about internal cohesion, density, and structural integrity. The fact that 3I Atlas remained intact during its high-speed passage past the Sun suggests a robust, relatively compact nucleus capable of enduring extreme environments, both in interstellar space and within the gravitational well of another star. Spectroscopic analysis of faint interstellar objects is always challenging, but 3I Atlas provided sufficient signal to detect several key signatures. Observers identified weak absorption bands corresponding to water ice and traces of carbon monoxide and carbon dioxide, indicating that volatile ices survived even after prolonged exposure to the harsh conditions of interstellar space. The low albedo, combined with these spectral features, points to a surface coated in carbonaceous material, likely processed by cosmic radiation over millions of years. Such layers would protect underlying ices from complete sublimation, allowing these volatiles to remain stable for vast durations. The resulting data not only provide a snapshot of the object's current state, but also offer insight into the long-term chemical evolution of material ejected from other planetary systems. The hyperbolic trajectory of 3I Atlas, coupled with its velocity exceeding solar system escape speed, enabled astronomers to study the dynamics of interstellar motion in situ. By modeling its orbital path backward in time, including perturbations from planetary encounters and the Sun's gravity, researchers attempted to identify candidate regions in the Milky Way where it may have originated. These models incorporate not only stellar motions, but also the gravitational influence of the galactic disk, nearby clusters, and molecular clouds. While the chaotic nature of galactic dynamics prevents a precise identification of a source star, statistical analyses suggest that it may have been ejected from a system containing massive planets capable of gravitationally scattering small bodies into interstellar trajectories. Simulations indicate that young, densely populated, star-forming regions are likely sites for such ejections, consistent with the object's inferred age and composition. 3I Atlas's brief visibility also illuminated the limitations and capabilities of modern astronomical surveys. Its discovery by the Atlas survey highlighted the importance of wide-field, rapid cadence observations for detecting fast-moving, faint objects. Once identified, coordinated follow-up from telescopes worldwide allowed for continuous monitoring across multiple wavelengths, providing a temporal and spectral record critical for understanding its behavior. The faintness of the object, combined with its rapid motion, demonstrates that many interstellar travelers likely go undetected each year. Observational biases favor the discovery of brighter, larger objects, meaning that smaller fragments like 3I Atlas may represent only the visible tip of a much larger population of interstellar material passing through the solar system. Each detected object informs statistical models, helping to constrain the number, size distribution, and composition of interstellar debris, and refining expectations for future discoveries by observatories such as the Vera C. Rubin Observatory. As the object receded, diminishing to the limits of detectability, astronomers examined its fading brightness to refine estimates of size, reflectivity, and dust content. The minimal activity observed suggests a surface with only modest volatile content or a protective layer of refractory material, limiting sublimation. The asymmetries in its light curve persisted, confirming the irregular, elongated structure inferred from earlier observations. These characteristics reinforce the notion that interstellar objects are diverse in shape, composition, and activity, reflecting the varied environments from which they originate. Each fragment, traveling across light years, carries with it a record of its parent system, the ejection process, and the interstellar journey itself, allowing scientists to read this information from light curves, spectra, and trajectories. Even after the departure of 3I Atlas from the inner solar system, its contribution to science remains profound. The collected observations serve as empirical evidence for models of planetary system formation, interstellar object ejection, and the long-term evolution of small bodies. By comparing its properties with those of Oumuamua and 2I Borisov, astronomers can examine patterns in composition, morphology, and activity, gradually constructing a framework for understanding interstellar matter on a population scale. The faint traces of dust and ice, combined with the trajectory data, enrich models of galactic material transfer, revealing how stars exchange debris over time and demonstrating the continuity between distant planetary systems and our own solar neighborhood. The journey of 3I Atlas, though fleeting in human timescales, encompasses the vastness of galactic processes. Its motion is dictated by gravity, shaped by collisions and radiation, and recorded in the subtle chemistry of its surface. By studying these details, scientists gain insight into the conditions of star-forming regions, the mechanics of planetary system ejection, and the physical changes that occur as objects traverse interstellar space. Each measurement, each spectral line, and each positional determination builds a cumulative picture of a world older than the Sun, traveling silently and invisibly until its brief intersection with our observational instruments. In this way, 3I Atlas serves not merely as an object of curiosity, but as a bridge connecting the distant past of another system to the present understanding of the galaxy we inhabit. Beyond the immediate solar environment, 3I Atlas continued its silent journey through the galaxy, a traveler among the stars, shaped by forces that operate over vast distances and immense timescales. Its interstellar history stretches back millions, perhaps billions of years, beginning in a system where gravitational interactions and planetary migrations were sufficient to eject it from its birth orbit. Massive planets can scatter smaller bodies with tremendous energy, and stellar encounters within dense clusters can further accelerate these objects, sending them on trajectories that escape the gravitational hold of their parent star entirely. Such mechanisms, well modeled in celestial dynamics, provide the framework for understanding how 3I Atlas, now distant and fleetingly observed, arrived at the Sun's neighborhood at precisely the moment astronomers were able to detect it. Exposure to the interstellar medium over these timescales has a profound effect on small bodies. Galactic cosmic rays slowly modify the chemistry of surfaces, creating a layer of complex organic compounds atop volatile-rich interiors. Though invisible to the naked eye, this layer absorbs and reflects sunlight differently than unprocessed ice, subtly influencing the measured albedo and spectral features. Sparse dust particles drifting in interstellar space erode surface irregularities over eons, smoothing edges, redistributing loose material, and slightly altering the object's shape. These processes, slow and cumulative, are recorded in the very structure and reflectivity observed during its passage through the solar system. The faint signals collected during its brief solar encounter allow scientists to connect these interstellar processes to measurable characteristics. Variations in brightness reveal tumbling motion and an elongated, irregular shape, while spectral absorption lines provide evidence for water ice and traces of carbon monoxide and carbon dioxide. The low overall reflectivity indicates a surface coated in carbon-rich materials, processed by cosmic rays and interstellar exposure, while the subdued outgassing reflects a combination of small size and depletion of near-surface volatiles. Each piece of information, though subtle, acts as a clue to the life history of a body that has crossed the gulf between stars. 3I Atlas also informs models of planetary system formation and debris ejection. Its size, composition, and orbital parameters suggest it was part of a population of small bodies scattered early in its parent system's evolution. Simulations of planetary scattering show that such objects are commonly ejected into interstellar space during the early phases of system development, particularly in systems with massive planets undergoing migration. Over time, these bodies drift through the galaxy, contributing to a hidden population that occasionally intersects the solar system, where precise observations like those of 3I Atlas provide rare empirical data. Comparisons with 1I Oumuamua and 2I Borisov highlight the diversity of interstellar visitors. Oumuamua exhibited non-gravitational acceleration with no visible coma, suggesting either outgassing below detection limits or unusual structure, while Borisov resembled an active comet with a visible tail. 3I Atlas occupies an intermediate space, faintly active, minimal outgassing, tumbling, and irregular. Its characteristics reinforce the understanding that interstellar bodies are not homogeneous. They span a spectrum of compositions, shapes, and responses to stellar heating, reflecting the diversity of the planetary systems from which they originate. Statistical extrapolations based on its detection provide insight into the prevalence of interstellar debris. The fact that 3I Atlas was discovered at all suggests a larger population of similar-sized bodies traversing the galaxy undetected. Survey biases imply that many smaller or darker interstellar objects likely pass unnoticed, invisible to current telescopic instruments. Each observation thus serves as a critical anchor for models of interstellar object frequency, size distribution, and composition, informing both theoretical expectations and the design of future observational campaigns. Even as 3I Atlas receded beyond the reach of Earth-based instruments, its legacy endures. The faint traces of dust and ice, the tumbling rotation, and the hyperbolic trajectory together provide a coherent narrative of an object shaped by ejection from a distant planetary system, sculpted by interstellar exposure, and briefly illuminated by the sun. These data points inform models of galactic material circulation, the mechanisms by which small bodies are scattered, and the chemical evolution of interstellar solids. In observing 3I Atlas, scientists witness a bridge between distant systems, connecting regions of the galaxy separated by light years, offering empirical evidence for processes that are otherwise inferred only through simulations or indirect observation. Ultimately, 3I Atlas exemplifies the profound interplay between observation and theory. The meticulous gathering of photometric and spectroscopic data, combined with orbital simulations, reveals the intertwined story of formation, ejection, and interstellar survival. Its brief visit reinforces the necessity of precise, coordinated monitoring of the skies, emphasizing the value of detecting and studying these rare emissaries from beyond our solar system. Each measurement is not merely a data point, but a window into the broader mechanisms governing the movement and evolution of material across the galaxy, revealing both the power and subtlety of gravitational dynamics, cosmic irradiation, and the chemical processes that shape small bodies on the grandest scales. The observational campaign surrounding 3I Atlas was unprecedented in both scope and coordination. Astronomers mobilized networks of ground-based telescopes across multiple continents, each instrument contributing unique capabilities. Optical observatories captured the changing brightness and subtle variations in light curves, while infrared telescopes measured thermal emission and provided insight into surface composition and temperature. Spectroscopic instruments, despite the faintness of the object, discerned the presence of water ice, carbon monoxide, and carbon dioxide, tracing the molecular fingerprints that reveal both its origin and the chemical processes it has endured. These combined datasets formed a cohesive picture, allowing scientists to move beyond general approximations and to quantify properties with precision, despite the object's fleeting visibility. As data accumulated, patterns emerged in its rotation and light reflectivity. Variations in the light curve confirmed an elongated, irregular shape, while the tumbling rotation indicated non-principal axis motion, likely a result of gravitational interactions prior to ejection or torques from prior sublimation events. Observations of minor asymmetries in brightness revealed small-scale surface heterogeneities, possibly regions richer in volatiles or coated with slightly different layers of carbonaceous material. These details, while subtle, contributed to understanding the evolutionary history of 3I Atlas, offering clues to processes that act over millions of years in interstellar space. Thermal models derived from infrared measurements provided further insight into the object's structure. Despite exposure to the sun during its brief inner solar system passage, surface temperatures remained low enough that sublimation was slow and limited, supporting the hypothesis of a protective crust formed over millennia of cosmic irradiation. Beneath this layer, preserved ices continued to contain water and simple carbon compounds, providing a chemical record of the environment in which the object formed. By integrating thermal modeling with spectroscopic data, researchers could infer both the surface and near-subsurface properties, piecing together a profile of the object's interior without direct sampling. The trajectory data offered a window into the dynamics of interstellar travel. Its hyperbolic orbit, high velocity relative to the Sun, and steep inclination allowed scientists to confirm an origin beyond the solar system. By simulating interactions with nearby stars, the galactic gravitational field, and potential ejection events, astronomers could narrow down likely regions of origin to young stellar clusters or star-forming regions where dynamical scattering is frequent. Though pinpointing a precise parent star remained impossible, these models provide probabilistic insight into the processes that launch material into interstellar space and sustain the population of wandering bodies throughout the galaxy. The faint coma observed during solar approach, though minimal, offered clues to the physical and chemical nature of 3I Atlas. Unlike the bright, easily observable tails of solar system comets, The outgassing here was limited, reflecting either a depletion of near-surface volatiles or an insulating surface crust. Nevertheless, even this subtle activity contributed to constraining dust-to-gas ratios and understanding the interaction between the object's surface layers and solar radiation. By comparing these measurements with solar system comets, scientists could place 3I Atlas within a continuum of cometary activity, highlighting both similarities and differences shaped by the interstellar environment. Each subsequent observation refined estimates of size, rotation, and composition, creating an increasingly detailed portrait. Light curve analysis indicated a nucleus several hundred meters in length, elongated and irregular, rotating in a manner consistent with prior cosmic perturbations. Spectral measurements confirmed the presence of volatiles beneath a carbon-rich surface, while thermal models validated assumptions about insulating layers that prevent rapid sublimation. These interconnected data points illustrate how multiple lines of evidence, when combined, yield a coherent understanding of an object never directly sampled, moving across the void between stars for eons. The implications of these findings extend far beyond the study of a single object. 3I Atlas exemplifies the ways in which interstellar matter contributes to the chemical and dynamical evolution of planetary systems. By tracing its properties and behavior, scientists gain insight into the diversity of planetary formation environments, the efficiency of debris ejection, and the conditions that small bodies experience while traveling through interstellar space. The knowledge gained informs not only the understanding of our own solar system's formation, but also the broader context of planetary system development across the galaxy. Even as 3I Atlas receded and faded from view, it left a legacy of data, models, and insight. Observational records continue to inform simulations of interstellar object populations, providing benchmarks for detection strategies and refining estimates of the frequency and characteristics of similar visitors. In its quiet passage, the object has bridged vast distances and long timescales, connecting human observation with the physical processes that govern the galaxy. Its journey, though measured in months within the solar system, represents millions of years of cosmic history, a testament to the dynamic and interconnected nature of material across interstellar space. As 3I Atlas continued to recede from the inner solar system, the focus shifted to analyzing the subtle details embedded in its fading signal. Even at great distances, slight variations in reflected sunlight provided information about surface roughness and compositional heterogeneity. Observers noted that the light curve maintained asymmetries consistent with its irregular, elongated shape, confirming that the tumbling motion persisted as the object moved away from solar heating. These ongoing observations, delicate and precise, allowed scientists to extend understanding beyond the brief window of peak visibility, capturing the gradual dimming and the resulting constraints on size, albedo, and potential residual activity. The physical characteristics inferred from the fading brightness indicated a core robust enough to withstand prolonged exposure to both interstellar and solar environments. Its density, inferred from the minimal changes in trajectory due to sublimation forces, suggested a solid, coherent body rather than a loosely bound aggregate. This structural integrity supports models of long-term survival during interstellar travel, where collisions with micrometeoroids, cosmic irradiation, and thermal cycling exert continuous but gentle forces. Over millions of years, such bodies endure, preserving both material composition and shape until chance alignment brings them briefly within the observational reach of an advanced planetary system. Simultaneously, spectroscopic data continued to inform understanding of chemical evolution. Even as signal strength waned, analysis revealed that 3I Atlas retained traces of water ice, carbon monoxide, and carbon dioxide beneath a dark, carbon-rich surface. This layered configuration, where volatiles lie beneath a refractory crust, is consistent with theoretical models of cosmic ray processing in interstellar space. Over time, exposure to high-energy particles alters surface chemistry, creating complex organics that insulate more volatile layers and preserve them for eventual sublimation under the influence of a nearby star. These patterns, though subtle, offer a glimpse into chemical processes that operate on scales far larger and longer than a human lifetime, reflecting both the history of the object and the environment through which it has traveled. The dynamics of its hyperbolic orbit were equally informative. With a velocity exceeding the Sun's escape speed, 3I Atlas illustrated the energetic consequences of ejection from another planetary system. Simulations incorporating gravitational interactions with massive planets, nearby stars, and the galactic potential helped constrain the possible regions of origin. These models suggested likely formation in dense, young stellar clusters where close encounters are common, and where gravitational scattering efficiently accelerates small bodies to interstellar speeds. Although pinpointing a precise parent star remained elusive, the combination of velocity, trajectory, and orientation provides probabilistic insights into the mechanisms responsible for populating interstellar space with such material. 3I Atlas's faint and brief activity during solar passage further informed comparative studies of small bodies. Unlike typical comets of the solar system, which develop visible tails and robust comet, this object displayed only minimal outgassing, consistent with either depletion of near-surface volatiles or the presence of an insulating crust. The contrast between its subdued activity and the pronounced displays of comets within the solar system emphasizes the diversity of small body responses to stellar heating. By situating 3I Atlas within this spectrum, astronomers refine models predicting activity levels based on size, composition, and thermal history, improving understanding of both local and interstellar populations. Observational campaigns also highlighted the challenges of detecting such objects. The faintness, rapid motion, and brief window of maximum visibility meant that even with coordinated efforts, only limited data could be collected during its closest approach. Yet each observation, whether photometric, spectroscopic, or astrometric, contributed to a comprehensive dataset that, when analyzed collectively, revealed a detailed and coherent picture of an interstellar traveler. These efforts underscore the need for continuous, wide-field monitoring to capture future interstellar visitors and emphasize the rarity and value of such opportunities. Even as it moved beyond the reach of telescopes, the implications of 3I Atlas's passage extend into theories of galactic matter exchange. By carrying chemical and structural records from another star system, the object serves as a messenger, bridging vast distances and timescales. Its composition, shaped by ejection, interstellar exposure, and brief solar interaction, offers empirical evidence that complements simulations of material circulation across the Milky Way. In studying this singular object, astronomers gain insight into the processes by which planetary systems shed debris, how this material survives interstellar travel, and the potential for such bodies to seed distant systems with building blocks of matter. The scientific reflection on 3I Atlas is therefore both specific and expansive. Each measurement contributes to understanding its individual properties, while collectively these observations illuminate broader processes governing small body evolution, interstellar dynamics, and the diversity of planetary systems. Its fleeting appearance emphasizes the scale of the galaxy and the rarity of direct observation, reinforcing the value of rapid, coordinated, and sensitive monitoring. In the quiet tracking of light, subtle spectral lines, and calculated orbits, the object's story unfolds with meticulous precision, bridging human curiosity with the vast, enduring processes that govern material between stars. The passage of 3I Atlas prompted renewed attention to the broader population of interstellar objects, highlighting the need to quantify both their frequency and diversity. Statistical models constrained by this detection and earlier observations, such as Oumuamua and 2I Borisov, suggest a vast number of small bodies traverse the galaxy, most too faint or small to be detected by current instruments. By extrapolating from survey capabilities, researchers estimate that every year numerous interstellar visitors pass through the solar system, their fleeting appearances offering rare opportunities to study material formed around distant stars. Each object, although individually subtle, contributes to a statistical framework gradually revealing the characteristics, sizes, and compositions of the interstellar population. Detailed analysis of 3I Atlas provides insight into the mechanisms that deliver such bodies from their parent systems. Models of planetary formation indicate that gravitational scattering by giant planets is highly efficient at ejecting small objects. Close stellar encounters in dense clusters can further accelerate material, imparting velocities sufficient to escape the host star's gravity. The observed hyperbolic trajectory of 3I Atlas is consistent with such ejection events, and its current velocity provides constraints on the energy distribution of ejected bodies in other planetary systems. By combining these dynamics with the object's physical and chemical properties, astronomers can link observable characteristics to the processes that govern interstellar material exchange. The chemical composition of 3I Atlas carries information about the environment of its origin. Spectral signatures confirm the presence of water ice and minor volatiles beneath a carbon-rich surface, suggesting formation in a cold, outer region of a planetary system. Exposure to cosmic rays over millions of years gradually modifies the surface, producing complex organic compounds that shield underlying ices. This layering, detectable through albedo variations and spectral absorption bands, acts as a record of interstellar processing, allowing scientists to infer both the initial conditions in the parent system and the cumulative effects of cosmic exposure. These insights reinforce the idea that interstellar objects are not merely inert fragments, but dynamic repositories of galactic chemical history. Observational comparisons with solar system comets further illuminate the uniqueness of interstellar bodies. While typical comets develop prominent tails due to sublimation of volatiles in the inner solar system, 3I Atlas exhibited only minimal activity, indicating a low volatile content near the surface or the presence of a protective crust. Its tumbling motion contrasts with the more regular spin of many solar system comets, implying prior gravitational perturbations or collisions. Such differences underscore the diversity of formation and evolutionary paths across stellar systems and demonstrate that interstellar objects can differ markedly from local counterparts while still obeying universal physical laws. The dynamics of interstellar travel itself play a role in shaping the characteristics of such bodies. The object's motion through the galactic potential, interactions with interstellar gas and dust, and sporadic collisions with micrometeoroids all influence its surface texture, chemical composition, and structural integrity. Over millions of years, these forces slowly erode features, distribute organic layers, and maintain stability in a delicate balance between exposure and preservation. Observations of 3I Atlas, therefore, provide empirical evidence for these long-term processes, allowing scientists to validate models of interstellar evolution and to refine predictions about the survival of small bodies on cosmological timescales. In addition to individual properties, 3I Atlas informs broader considerations of galactic matter circulation. Small bodies ejected from planetary systems act as carriers of material across light years, linking the evolution of distant stars with the solar system. Their chemical makeup can seed future systems, and their presence indicates that planetary formation is not an isolated process, but part of a larger, interconnected galactic environment. Each interstellar object captured by observation, even momentarily, reinforces the understanding that the galaxy is not a static collection of stars, but a dynamic network through which matter constantly moves, carrying chemical signatures, physical histories, and evidence of processes that unfold on timescales far beyond human perception. As 3I Atlas faded from view, the cumulative observations continued to influence planning for future detections. Its brief appearance demonstrated the necessity of sensitive, wide-field surveys capable of rapid detection and follow-up, emphasizing the importance of global coordination among observatories. Data collected from this singular encounter will inform not only models of interstellar object populations, but also strategies for capturing more comprehensive datasets in the future. By understanding the limitations and successes of current detection methods, astronomers can refine techniques to maximize information retrieval, ensuring that subsequent interstellar visitors are studied with even greater precision and depth. In this context, 3I Atlas serves as a reminder of both the rarity and significance of such encounters. Its passage highlights the interplay between observation, theory, and modeling, revealing a nuanced picture of interstellar dynamics, chemical evolution, and planetary system interaction. Every measurement, from light curve to spectrum, contributes to a layered understanding of the object itself and of the broader galactic environment. The scientific narrative emerging from its brief transit extends far beyond a single observation, informing theories that link formation, ejection, survival, and eventual observation across the vast scales of space and time. Over the vast distances it traversed before encountering the solar system, 3I Atlas was subjected to the subtle but persistent forces of the interstellar medium. Galactic cosmic rays continuously bombarded its surface, altering chemical bonds and producing a thin layer of complex organics. This irradiation slowly darken the surface while leaving the interior largely unaltered, a testament to the shielding properties of accumulated refractory material. Minute collisions with micrometeoroids, though individually insignificant, gradually reshaped surface topography, smoothing sharp edges and redistributing loose material. Together, these processes preserved a record of both the interstellar environment and the object's resilience, encoding a multi-million-year history that could be read through careful observation and modeling. The spectral signatures of 3I Atlas provide insight into its chemical evolution. Observations captured weak absorption bands consistent with water ice, along with traces of carbon monoxide and carbon dioxide. These volatiles, though present in limited amounts, indicate that the object formed in a cold region, likely analogous to the outer regions of planetary systems, where temperatures remain low enough for such ices to condense. Overlaying these ices, the carbonaceous crust produced by cosmic ray processing not only protects the underlying material, but also contributes to the object's low reflectivity, a characteristic that challenges detection, yet preserves chemical integrity over immense timescales. Physical modeling of 3I Atlas also revealed the interplay between shape, rotation, and thermal effects. Its elongated and irregular geometry, combined with tumbling rotation, leads to uneven heating by sunlight during perihelion passage. Thermal gradients across the surface influence sublimation rates, producing only minimal outgassing, insufficient to generate a significant coma or tail. These observations, when combined with data on size, density, and composition, allow astronomers to reconstruct internal structure and infer mechanical strength. The evidence suggests a compact, coherent body capable of withstanding both interstellar travel and the stresses encountered during its solar approach. The object's trajectory through the solar system offered additional information about the dynamics of interstellar travel. The hyperbolic orbit, with an inbound velocity exceeding solar escape speed, aligns with theoretical models of gravitational ejection from distant planetary systems. Simulations of such ejections indicate that interactions with massive planets or close encounters with other stars can impart sufficient energy to small bodies, sending them on trajectories that carry them across the galaxy. By analyzing these dynamics, astronomers gain insight not only into 3I Atlas's likely origin, but also into the broader mechanisms responsible for populating interstellar space, with small bodies capable of surviving millions of years in transit. Comparisons with solar system comets provide a framework for interpreting observations, whereas many comets develop visible tails driven by sublimation of abundant volatiles. 3I Atlas exhibited only faint activity, suggesting either depletion of surface volatiles or the presence of an insulating crust. Its tumbling motion contrasts with the more regular spin of many solar system comets, indicating prior perturbations or collisions. These distinctions highlight the diversity of small bodies across stellar systems, reflecting differences in formation, evolutionary history, and exposure to environmental forces, while demonstrating that universal physical laws govern behavior across contexts. The observational challenges presented by 3I Atlas also underscore the importance of survey design. Its faintness, brief window of maximum brightness, and rapid motion through the sky required wide-field, high-cadence monitoring and rapid coordination among global observatories. Data from optical, infrared, and spectroscopic instruments were integrated to produce a detailed, multifaceted portrait. Despite these limitations, this collaborative effort illustrates how the combination of precision, coordination, and sensitive instrumentation can transform brief encounters into rich sources of scientific insight. In a broader context, 3I Atlas exemplifies the role of interstellar objects as carriers of galactic information. Its chemical composition, physical structure, and trajectory collectively encode information about planetary formation, ejection processes, and interstellar evolution. Each parameter measured contributes to a deeper understanding of material transport across the galaxy, revealing the continuity of matter between distant systems and the solar system. Observing and analyzing such bodies allow scientists to trace connections between formation environments, interstellar survival, and eventual solar system encounters, offering empirical grounding for theories that otherwise rely on simulation or inference. Even as the object receded into the outer solar system and beyond, fading beyond the reach of telescopic detection, the scientific value of its passage remains. The accumulated observations inform not only models of interstellar populations and planetary system dynamics, but also strategies for future detection, emphasizing the need for sensitive, global, and rapid response observational networks. Through these efforts, astronomers can maximize the scientific yield of rare encounters, extracting insights from subtle signals and ephemeral appearances. In this sense, 3I Atlas serves as both a messenger from another system and a catalyst for refining methods that will capture the next interstellar visitor, ensuring that the story of material moving between stars continues to unfold with increasing clarity and detail. Extending beyond its individual characteristics, 3I Atlas informs a growing understanding of the population of interstellar objects traversing the Milky Way. While only a few such bodies have been detected directly, statistical models informed by their velocities, trajectories, and brightness suggest a far greater abundance. Many remain invisible to current instruments, their small sizes or dark surfaces rendering them undetectable except under optimal observational conditions. By analyzing the detection of 3I Atlas in the context of survey coverage and efficiency, scientists estimate the frequency, size distribution, and compositional diversity of interstellar debris, establishing a foundation for predicting future encounters. The survival of interstellar objects over millions of years raises important questions about the physical processes that preserve them. Cosmic irradiation, micrometeoroid impacts, and exposure to the galactic medium all act to alter surfaces, yet these bodies endure with structural integrity sufficient to traverse light years unfragmented. 3I Atlas demonstrates that small bodies can retain both volatile content beneath protective layers and mechanical coherence despite prolonged interstellar exposure. Its preservation underscores the balance between erosive forces and the protective effects of accumulated refractory layers, offering empirical evidence to validate models of interstellar object longevity and chemical evolution. Chemical analysis of 3I Atlas reinforces these conclusions. Weak but discernible absorption bands indicate retained water ice and minor volatile compounds beneath a dark, carbonaceous crust. This stratification points to both the conditions of its formation, likely in the cold outer regions of a planetary system, and the cumulative effect of cosmic radiation during interstellar transit. Each spectral signature acts as a temporal record, preserving information about the object's origin and the galactic environment through which it has traveled. By integrating these chemical insights with dynamical modeling, astronomers construct a coherent narrative of the object's multi-million-year journey. Comparative studies with other interstellar visitors, including Oumuamua and Tuki Borisov, highlight the diversity inherent in objects originating outside the solar system. Whereas Oumuamua displayed extreme elongation with no visible cometary activity, and Borisov resembled a more conventional comet with active sublimation. 3I Atlas exhibited subdued activity and tumbling rotation. Its intermediate behavior emphasizes that interstellar objects cannot be assumed to resemble solar system analogues, illustrating a range of evolutionary histories and compositions shaped by unique ejection processes, interstellar exposure, and thermal histories. Such comparisons refine theoretical models of interstellar debris, helping to anticipate the properties of future visitors and improving the interpretation of observational data. The dynamics of interstellar travel itself influence both structure and composition. As 3I Atlas moved through the galactic medium, collisions with dust and micrometeoroids, coupled with irradiation from cosmic rays, gradually altered its surface, creating a thin layer of processed organics while preserving subsurface volatiles. The interplay of these forces maintains a subtle balance between erosion and preservation, enabling small bodies to survive over vast distances. The study of these processes in 3I Atlas provides a tangible example of how interstellar environmental effects shape the observable properties of small bodies, validating theoretical predictions and informing expectations for other interstellar objects. The broader implications of 3I Atlas extend into the understanding of planetary system evolution. By connecting observed properties with models of formation, ejection, and interstellar survival, scientists can infer the efficiency of material exchange between planetary systems. Gravitational scattering by giant planets, close encounters with neighboring stars, and dynamical instabilities during system formation all contribute to ejecting material into interstellar space. The properties of 3I Atlas, including its composition, rotation, and trajectory, offer empirical constraints on these processes, allowing researchers to bridge the gap between theory and observation. Even as it disappeared into the outer reaches of the solar system, the legacy of 3I Atlas persists in the accumulated scientific record. Observations of its light curve, spectra, and trajectory form a foundation for future studies, providing benchmarks against which subsequent interstellar discoveries can be compared. Its brief presence demonstrates the importance of continued investment in observational infrastructure, wide-field surveys, and coordinated global networks capable of capturing ephemeral visitors. The knowledge gained from this single object amplifies our understanding of interstellar dynamics, chemical evolution, and the diversity of planetary systems, highlighting the interconnectedness of seemingly isolated events across galactic scales. Reflecting on its journey, 3I Atlas embodies the quiet persistence of material moving across the cosmos. Its physical integrity, subtle chemical record, and precise motion all speak to processes that operate on scales both immense and gradual. By observing, analyzing, and contextualizing its properties, astronomers extract a narrative that spans millions of years and countless light years, linking the formation environments of distant stars to the solar system and to the human endeavor of scientific inquiry. In the gentle tracking of faint light and the meticulous measurement of its passage, the story of 3I Atlas continues to illuminate the dynamic and interconnected nature of our galaxy. The prolonged survival of 3I Atlas in interstellar space illuminates the delicate balance between exposure and preservation. Cosmic rays continuously penetrate its outer layers, triggering chemical transformations that generate complex organics while leaving deeper ices largely intact. These surface layers, darkened and carbon-rich, act as both a record of galactic conditions and a protective barrier, preventing rapid sublimation during the brief solar encounter. Minute impacts from interstellar dust contribute to subtle erosion, reshaping the surface texture over millions of years. Yet the core remains coherent, demonstrating the mechanical resilience necessary to endure the vast voids of the galaxy. Modeling the thermal and rotational behavior of 3I Atlas provides further insight into its physical integrity. Its irregular shape, combined with tumbling motion, results in uneven heating, producing localized sublimation, but insufficient to significantly alter its mass or trajectory. The faint, limited activity observed confirms the presence of an insulating crust that moderates the effects of solar radiation. Through these analyses, scientists are able to infer both internal structure and material properties, revealing a compact, cohesive body formed under conditions similar to those of cometary bodies, yet exposed to a far harsher interstellar environment. Chemical signatures preserved in the surface and near subsurface layers carry the imprint of its origin. Water ice, carbon monoxide, and carbon dioxide, detectable despite faint signals, indicate formation in a cold, distant region of a planetary system, likely far from the parent star. Over time, exposure to cosmic rays modified the surface chemistry, producing organic compounds and altering albedo characteristics. The combination of original volatiles and processed organics provides a chronological record of the object's journey, bridging the gap between its formation billions of kilometers from any star and its brief, observable passage through the solar system. 3I Atlas's hyperbolic trajectory exemplifies the dynamics of interstellar travel. Its velocity, exceeding solar escape speed, aligns with ejection mechanisms from distant planetary systems, where gravitational scattering by massive planets or close stellar encounters imparts sufficient energy to small bodies. By analyzing its trajectory and comparing it with models of galactic dynamics, astronomers gain insight into the likely environments of origin, the frequency of ejection events, and the distribution of material moving between stars. Even without pinpointing a specific parent system, these models allow a probabilistic understanding of how interstellar objects populate the galaxy. Comparisons with solar system, comets, and asteroids reinforce the distinctiveness of interstellar visitors. Whereas comets within the solar system typically display predictable rotational patterns and active outgassing, 3I Atlas exhibits irregular tumbling and only minimal sublimation. Its dark, carbon-rich surface differs from the often brighter ice-laden surfaces of local comets, reflecting both its formation conditions and the cumulative effects of interstellar exposure. These contrasts highlight the variety of small bodies across stellar systems and emphasize that interstellar objects carry unique evolutionary histories shaped by conditions unattainable within a single planetary system. observational campaigns provided a wealth of empirical data despite the challenges posed by faintness and rapid motion. Coordinated photometric, spectroscopic, and astrometric measurements enabled reconstruction of shape, size, rotation, and composition. Infrared observations offered insight into thermal properties and potential subsurface volatiles. Light curve analysis revealed asymmetries consistent with tumbling rotation and irregular morphology. Each data point, while individually subtle, contributes to a cumulative understanding, demonstrating the power of coordinated global observation and the precision of modern astronomical instrumentation. In the context of galactic material exchange, 3I Atlas serves as a messenger, connecting distant planetary systems with our own. Its preserved chemical and physical characteristics encode information about formation environments, ejection dynamics, and interstellar processing. Through careful observation, scientists can read this record, tracing the history of material across light years and millions of years. By linking individual observations with models of galactic dynamics and planetary formation, astronomers gain insight into the movement of matter on a scale that extends far beyond the solar system, illuminating the interconnected nature of the Milky Way. Reflecting on its brief yet scientifically rich encounter, 3I Atlas exemplifies the value of meticulous, patient observation. Its passage demonstrates that even small, faint objects carry profound information about distant systems, interstellar processes, and the continuity of matter across vast cosmic distances. Each measurement, from faint spectral lines to precise orbital calculations, contributes to a broader understanding of interstellar travel, planetary system evolution, and the subtle chemical and physical processes that shape small bodies in the galaxy. In observing this object, scientists witness both the resilience of interstellar material and the capacity of human inquiry to decipher the history encoded within a tiny fragment of cosmic debris. In the quiet that follows its departure, the implications of 3I Atlas endure. The collected data continue to inform models of interstellar populations, the efficiency of ejection mechanisms, and the long-term preservation of chemical and physical characteristics. Its existence, observed for only a fleeting moment, reinforces the notion that the galaxy is a dynamic, interconnected system in which even the smallest bodies carry information across incomprehensible distances and timescales. Through the study of such objects, humanity gains not only knowledge of distant worlds, but also a perspective on the delicate processes that link the countless stars and planetary systems scattered across the Milky Way. Looking beyond the immediate observations, 3I Atlas illuminates the intricate connections between planetary system dynamics and the wider galactic environment. Its existence demonstrates that material from one star system can journey across light years, carrying information about formation, chemical composition, and mechanical history. By studying its properties, astronomers gain insight into the efficiency and mechanisms by which small bodies are ejected, the influence of giant planets on orbital architecture, and the statistical likelihood that other systems similarly shed debris. Each data point, whether it pertains to tumbling motion, spectral features, or orbital inclination, enriches the framework for understanding how interstellar material circulates and evolves over cosmological timescales. The implications for chemical evolution are equally profound. Organic compounds synthesized under cosmic ray irradiation on the surface of 3I Atlas reveal the subtle transformations that occur during interstellar transit. Beneath these protective layers, preserved ices retain a record of the molecular composition of the object's birth environment. The combination of altered organics and intact volatiles exemplifies the dual processes of alteration and preservation, demonstrating how even prolonged exposure to interstellar space does not erase the fundamental chemical fingerprints of origin. These insights inform not only the study of interstellar objects, but also broader models of material transport, chemical evolution, and the potential for prebiotic chemistry across the galaxy. Trajectory analysis further underscores the significance of interstellar dynamics. The hyperbolic path of 3I Atlas, coupled with its high relative velocity, confirms that gravitational scattering is an efficient and common mechanism for ejecting material from planetary systems. Simulations of stellar encounters and planetary migrations show that small bodies can achieve velocities sufficient to escape host stars, entering stable trajectories through the galaxy. These dynamics, when correlated with physical and chemical data, allow scientists to construct a holistic understanding of the processes that generate and maintain populations of interstellar objects, bridging gaps between theory and empirical observation. The observed faint activity, minimal as it was, provides additional nuance. Even slight outgassing during perihelion offers clues to the distribution and depth of volatiles within the body. By combining thermal modeling with light curve variations, researchers can infer insulation properties, porosity, and surface composition. Such analyses demonstrate that even small, dim, and briefly observed objects contain complex internal structures, shaped both by their formation and by the prolonged journey through interstellar space. Every subtle variation in brightness and spectral absorption becomes a window into processes that unfolded over millions of years, connecting microscopic chemical changes with macroscopic physical characteristics. From a broader astronomical perspective, 3I Atlas contributes to understanding the movement of matter between star systems. Its journey emphasizes that the galaxy is a dynamic environment where material is exchanged, recycled, and redistributed on scales both vast and gradual. Observing these exchanges provides insight into the diversity of planetary system outcomes and the potential for chemical seeding between distant systems. Each interstellar object observed, though ephemeral, is a data-rich emissary that links formation environments with distant locations across the Milky Way, offering tangible evidence of the processes that shape galactic structure and evolution. As its faint light disappeared into the vastness beyond the planetary orbits, the value of 3I Atlas persisted in the datasets, models, and simulations it informed. Astronomers now use its passage as a benchmark for future detection, refining techniques for identifying transient interstellar bodies, optimizing survey coverage, and integrating multi-wavelength observational strategies. Its existence underscores the importance of rapid response, global collaboration, and sensitive instrumentation in capturing fleeting glimpses of objects that, though small, carry immense scientific significance. Ultimately, the passage of 3I Atlas offers a quiet but profound reminder of the interconnectedness of cosmic systems, from its formation in a distant planetary system, through ejection and survival across the galaxy, to the brief moment it became observable in the solar system. Every aspect of its journey is recorded in its structure, composition, and trajectory. By studying these attributes, scientists not only reconstruct the history of a solitary interstellar traveler, but also gain insight into the forces, processes, and interactions that govern the movement of matter across the Milky Way. Its story exemplifies the continuity of physical laws, the resilience of matter, and the capacity of careful observation to reveal the extraordinary in the apparently mundane. In the stillness following its departure, 3I Atlas leaves a lasting impression on human understanding. Its faint, fleeting passage reminds us that even the smallest fragments carry the weight of cosmic history, bridging star systems and offering empirical testimony to processes unfolding over millions of years. Observing, measuring, and modeling such objects connects humanity with a universe in constant motion, where material, energy, and chemical signatures flow silently across unimaginable distances. In the subtle glimmer of light that once reached Earth, the story of interstellar travel, survival, and scientific discovery continues to resonate, quietly affirming both the resilience of matter and the enduring pursuit of knowledge. The lingering lessons of 3I Atlas extend beyond the object itself, influencing both methodology and perspective. By observing its brief passage, astronomers refine not only models of interstellar populations, but also strategies for future exploration. Coordinated global monitoring, high-sensitivity instrumentation, and multi-wavelength observation techniques all gain validation through the successful characterization of this solitary traveler. Each incremental measurement, whether a minute change in brightness, a faint spectral absorption, or a calculated orbital perturbation, adds to a comprehensive understanding that transcends the individual event, contributing to an evolving framework for studying material in transit across the galaxy. In terms of chemical insight, the preserved volatiles beneath a carbon-rich surface illustrate the resilience of matter exposed to prolonged cosmic forces. Water, carbon monoxide, and carbon dioxide ices remain detectable, offering a chemical snapshot of a distant planetary system's outer regions. The surface organics, generated through millions of years of cosmic ray exposure, narrate the subtle transformations that shape interstellar bodies over time. Together, these layers act as a chronicle of both origin and journey, encoding environmental history that is only accessible through meticulous observation and analysis. The structural and rotational characteristics of 3I Atlas further inform understanding of small body mechanics under interstellar conditions. Its elongated, tumbling form reflects the cumulative effects of ejection, minor collisions, and gravitational perturbations prior to solar encounter. Thermal modeling during perihelion passage demonstrates how uneven heating influences sublimation and activity, confirming that the body's modest outgassing is constrained by a protective crust. These dynamics reveal the interconnectedness of physical structure, chemical composition, and environmental exposure, emphasizing the degree to which interstellar processes shape observable properties over immense distances and timescales. Beyond scientific data, the journey of 3I Atlas symbolizes the continuity of cosmic processes, from formation in a distant stellar system to ejection into the interstellar medium and eventual passage through the solar system. The object's trajectory illustrates the ongoing movement and redistribution of matter across the Milky Way. Each step of its voyage encapsulates physical laws operating on scales far beyond human perception, linking discrete planetary systems within a broader galactic context. By studying this journey, astronomers gain insight into the forces that connect stars, planets, and interstellar debris into a dynamic, interrelated system. The reflective significance is subtle yet profound. Observing 3I Atlas allows humanity to witness a fragment of matter that has traveled for millions of years, silently traversing the void before becoming briefly perceptible. Its passage reminds us of the delicate persistence of matter, the hidden dynamism of the galaxy, and the capacity of human curiosity to uncover stories encoded in faint light and subtle motion. In the careful measurement and interpretation of these signals, scientists translate physical reality into knowledge, connecting distant cosmic events with human understanding. As the object recedes beyond the reach of detection, its contribution to knowledge persists. The data, models, and insights derived from 3I Atlas inform future observational campaigns, refine theoretical predictions, and enrich our understanding of interstellar processes. Its fleeting presence underscores the rarity of such opportunities and the necessity of preparedness, precision, and collaborative effort in capturing the subtleties of objects that traverse the solar system briefly before vanishing into the galactic expanse. Ultimately, 3I Atlas exemplifies the intersection of cosmic endurance and human inquiry. Its structure, composition, and trajectory collectively tell a story that spans star systems and light years, bridging the silence of interstellar space with the focused observation of astronomers. In witnessing and interpreting its passage, we gain insight not only into the object itself, but into the broader mechanisms that shape planetary systems, distribute matter across the galaxy, and preserve chemical and physical histories over cosmic timescales. Its journey, measured in light years and millions of years, becomes a narrative accessible to human understanding through careful observation and scientific reasoning. In the quiet aftermath of its passage, a sense of calm reflection emerges. The faint light once detected, the meticulous data collected, and the analytical models derived converge into a coherent story, offering both scientific insight and contemplative closure. 3I Atlas has moved on, continuing its journey through interstellar space, while the knowledge it imparted remains a testament to the persistence of matter and the enduring curiosity of those who study it. Its voyage, though silent and invisible to the naked eye, resonates through the careful work of astronomers, reminding us that even the smallest fragments of the cosmos carry histories, secrets, and connections that span the Milky Way.